Section 1.6 is about statistical modeling, scientific inspection, and graphical diagnostics. While statistical methods cannot generate sufficient evidence to characterize the population totally, sets of data are often used to learn about certain properties. Often, a summary of a collection of data using a graphical display can provide insight regarding the system from which the data were taken. In this section, we will look at 4 different ways to summarize or present data. Our first plot is the stem and leaf plot. This is an interesting plot that keeps all of the data listed. There are 4 main steps in drawing a stem and leaf plot. Number 1, select one or more digits for the stem values. The trailing digit becomes the leaf. Number 2, list the stems in a vertical ascending column. Then add a vertical line. Number 3, record the leaves in ascending order beside the corresponding stem. And lastly, 4, indicate the magnitude of the displayed numbers. That is, define a key. We'll do an example that shows what one of these stem and leaf plots looks like. Here's an example. The flexural strength of 10 concrete cylinders measured in megapascals to the nearest tenth are listed here. Construct a stem and leaf plot for the data. All right, so taking a look at our data, we see we have 10 observations, and we have a ones place, and we have 1 decimal place. We need to understand what our data looks like. So let's take a look at the range. So the smallest one looks to be 5.8, and our largest, looking at it, looks like it is 9.2. So for part 1, select one or more digits for the stem values, and the trailing digit becomes the leaf. So our stem values are going to range from 5 to 9, and then our leaves are going to be this decimal place. All right, so let's go ahead and start our stem and leaf plot. So we'll have stem written here. And our stems, as I said before, are going to be 5 through 9. And so part 2 says to list our stems in a vertical ascending column. So 5, 6, 7, 8, and 9. And then it also says to add a vertical line. Part 3 says to record the leaves in ascending order beside the corresponding stem. So what we do here is we look for all the data that is 5 point something. So the only piece of data that is 5 point something is 5.8. So we put an 8 right there. Next, we look at the 6. So we have a 6.1. We have a 6.6, and that looks like that's what we have. So in ascending order, we have a 1 and a 6. So we place a 1 and a 6 here. So just looking at this, we see that we have a 5, 8. That represents 5.8. Here we have 6 with the line 1, 6. So this is 6.1 and 6.6. Let's finish this out. We have a 7 next. So taking a look at all our data with 7 point something, we have a 7.8, a 7.1, a 7.2. Continuing down, we have a 7.0. So looking at the decimal places there, we should see that we have a 0, we have a 1, we have a 2, and we have an 8. So that represents 7.0, 7.1, 7.2, and 7.8. Let's see. 8. We have an 8.3 and an 8.3. Well, we've got a duplicate there, which is great. We still write it down because we want to show all of our data. Don't want to lose anything. So we have an 8.3 and an 8.3. And then finally, any data that starts with a 9, we have a 9.2, and it looks like that's all we have. So we have a 9, and we put that 2 right there for our 9.2. Some things to notice, we're not quite done, but some things to notice is that these are all in one line, and then these are in one line, and if there were more data here, we would have these line up and these line up. All right, so it helps us to create a picture of what our data actually looks like. Okay, so final step is indicate the magnitude of displayed numbers, and in other words, a key. So we come over here and write key, and you can simply write 5 line 8 is 5.8. So that describes exactly what we have on our stem and leaf plot. One last thing to note. The plot doesn't only list all of the data, it also shows you what it looks like pictorially. Because you can see on the side, if you look sideways at it, you can see that most of the data lies here in the middle, and as it gets further away, there's less of it. So if you could take this slide and turn it on its side, it would kind of look like a histogram, which is what we will show you in a little bit. Sometimes for really large data sets, the stems are often split up. In this picture here, we have the stem being split into 2. So for example, this 6 I have listed twice, so 6.0 through 6.4, all that data would be listed here, and then 6.5 through 6.9 would be listed here. And depending on the amount of data, you may have 3 6s and 3 7s and 3 8s and 3 9s. All depends on the data, how much data you have. And the reason you do this is so that the data doesn't list way out there and not give you much of a description. The second display is the frequency distribution and relative frequency distribution. Here, data are grouped into different classes or class intervals, usually of uniform width. In table format, the frequency at which the data fall into each class is noted. Then the relative frequency is obtained by dividing each class frequency by the total number of observations. And we'll take a look at an example next. Let's take a look at an example. Construct a frequency distribution and relative frequency distribution for the flexural strength data above. So in order to do this, we're going to make a table, and we'll start by making the column titles. So the first column we're going to put is class interval. The next one is class midpoint, which we don't use too frequently, but we'll put it in here anyway. The next will be frequency. And the last one, relative frequency. Okay, so for the class interval, we already know that our data goes from 5.8 to 9.0, and we want our class intervals to be very consistent. So I'm going to make my class intervals go from 5.0 to 5.9, 6.0 to 6.9. For the class midpoint, we take the midpoint of the consecutive left endpoints. So for example, 5.0 and 6.0 are the left two endpoints. So the first class midpoint is the midpoint of 5 and 6, so we have 5.5. The next two are 6 and 7, so it's 6.5, and so forth. For frequency, what we want is to find out how many pieces of data are in each one of those class intervals. So for the very first interval, 5.0 to 5.9, we take a look at our data and we see which data points fall in that interval. If you take a look, you should see that there is only one piece of data, 5.8. So frequency is 1. For the next interval, we have 6.0 to 6.9. And there are two pieces of data, 6.1 and 6.6. So there are two pieces of data. For data between 7.0 and 7.9, there are 4. We have 1, 2, 3, and 4. Between 8 and 8.9, there are 2. And we have 9.2, so there's only one piece of data that falls in that class interval. So that is your frequency distribution right there. To get the relative frequency distribution, we need to divide the frequency by the total number of data points. And we have 10 pieces of data up there. So our relative frequency is 1 divided by 10, or 0.1, 2 divided by 10, or 0.2, 4 divided by 10, which is 0.4, 2 divided by 10, 0.2, and 1 divided by 10, which is 0.1. And so that is your relative frequency distribution. Just taking a look at the relative frequency distribution, we're going to use these numbers for our next display, which will be a histogram, and we'll be doing a relative frequency histogram. So you'll see these numbers again, the 0.1, 0.2, 0.4, 0.2, and 0.1. Sorry. Next up is the histogram. A histogram is a graphical display of a frequency distribution or relative frequency distribution. So let's take a look at how to construct one. What we do is we draw axes, and on the bottom axis we're going to put our class interval. So it starts with 5, 6, 7, 8, 9, and we're going to have to go all the way up to 10 to make sure that we include that last data point, 10. The height of our relative frequency histogram are just going to be those numbers that we got on our relative frequency distribution. So we have 0.1, 0.2, 0.3, and 0.4. So if you'll look back at your relative frequency distribution, you would see that for the class interval between 5 and 6, we went up to 0.1. For between 6 and 7, the relative frequency was 0.2. So our histogram is going to go up to 0.2. Between 7 and 8, it went all the way up to 0.4. Between 8 and 9, it was 0.2. And finally, between 9 and 10, it was 0.1. So this shows you what the data actually looks like. If you go back and look at your stem and leaf plot, it also looks very similar to this. It has the data, largest amount of data here in the middle, and as you go further away from that middle, you see that the data goes down. There's less data out here than there is right here in the middle. It has a shape to it, and if you take and draw a curve over the top of it, whoops, this is a terrible picture of a curve. Let's try that again. You'll see that this is very mound shape, and some people would call it normally distributed. The shape of a histogram yields important information regarding the distribution. We'll take a look at 3 different shapes. From the example before, I showed you the shape of that histogram, and it was symmetric. So that's the first one we'll look at. Its data, if you put a histogram in there and drew across the top, would look like this. Very mound shape, very symmetric. Its mean is right in the center, as well as its mode. There are other shapes. One is called skewed left. And that's where you have most of your data. And then there's some outliers that push the tail out to the left. What happens then with the mean, if you think about having an outlier, the outliers affect the mean. And what happens is that that mean gets pulled out towards those outliers. So the x-bar is going to get pulled away from the rest of the data, where the median is going to stay right with the rest, with the center of the data. The third type, I'm sure you can guess, is skewed right. And its tail goes out to the right. And its mean is affected by that and is pulled out to the right, and its median is not affected by it, and it is centered with its data. So you can see with skewed left data, x bar is less than the median. For skewed right data, x bar is greater than the median. The last display is the box-and-whisker plot. This is a graphical display that shows the location of the center with a bar, variability using interquartile range, so it'll show you a range of data, and it will show whether it's symmetric or not, as well as outliers. I think our book shows it usually in this horizontal position, but you'll also see it often in a vertical position. So one of the things that we need to be able to draw a box and whisker plot is to find the median. And the median, we've already discussed how to find that. That is x with a tilde over it. It is inside the box. And it represents the 50th percentile. So I'll just take a little arrow. It's that point right there. The interquartile range, represented as IQR, equals the 75th percentile minus the 25th percentile. And it is the width of the box. So the 75th percentile is there. The 20th percentile is there. And the width of the box would be the difference between those. Outliers are the data values unusually far from the rest of the data. It's any data that is more than 1.5 times IQR, the interquartile range, beyond the box. And finally, the last bit to the box and whisker plot is drawing the whiskers. The whiskers go to the min and max that are not outliers. So we have the min stops there, the max stops there, and then if we had some outliers, they would be stars or dots or circles out here. Here's an example from the text. Listed here are the nicotine content in a random sample of 40 cigarettes. Now, to draw a box and whisker plot, we first need the median and the 25th percentile and the 75th percentile. So if you recall, in calculating the median, you need to have your data ordered from smallest to largest so that you can find which piece of data is right in the middle. One of the handy displays of the stem and leaf plot, not only does it show us the nice shape of the data, as you can see here, it shows you the shape of the data. It also puts all the data in order. So listed up here, the data is not in order. It's just listed, 1.9, 0.85, so forth. So the stem and leaf plot, and this particular stem and leaf plot, the decimal place is 1 digit to the left of the bar. So for example, this one right here, where it has 10 pipe 9, that is 1.09. So that's our first piece of data right there. So it's all ordered for us. So we'll be able to easily find the middle data and be able to then find the 25th and the 75th percentile. So to find our median, we know we have 40 pieces of data. That means there is no middle piece, but there are two middle pieces. And those two middle pieces are right here, right here. So we have 1.75 and 1.79. So what we do is we add them and divide by 2. So we take the middle, the average of the middle 2. So that value right there is 1.77. So our median is 1.77. To come up with the 25th percentile, the 25th percentile is simply the median of the first half of the data. So we will just take this section of the data and find the median of that. So we're going to make it called P25, and we're going to find the middle of that. So there's 20 values there. Therefore, the middle is going to be between 10 and 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So our value right there is 1.63 and 1.64. We're going to divide that by 2, and we'll get 1.635. Similarly, we will do that for P75, and what we come up with is actually 2.0. So that's a good start. Okay, so I brought our three statistics over from our previous page. We're going to start to draw a box and whisker plot. So I'm going to just put my x-axis right here. And I'm going to put some of these labels. So I'm going to start with my 1.77, that's my median. And then I have a 1.635 here. And then a 2 somewhere over here. I can already start drawing my box. It goes from 2 down to 1.635, and I have a bar right in the middle for the 1.77. All right, so next I need to calculate my interquartile range, and the interquartile range is the 75th percentile, so 2 minus the 25th percentile, 1.635. That equals 0.365. Okay. Next, I need to find out if I have any outliers. So I need to take a look at, from my box endpoints, whether 1.5 times my interquartile range, if there's any data that lies outside of those two spots. So I'm going to take and look at 1.5 times 0.365. That equals 0.5475. So any outliers will be anything greater than 2 plus 2.5475, which equals 2.5475, or less than the bottom of the box, 1.635 minus 0.5475, and that equals 1.0875. So we need to see, are there any data points that satisfy the outliers? And taking a look at the data, I do indeed see something. Let's see here. I have 2.55. It's just a little bit bigger, but it is out there. So we have somewhere out here, 2.55 is an outlier. And let's see if I have anything that is less than 1.875. And I definitely have something less than 1.875. I have two values. I have 0.72, 0.72, and 0.85. All right, and so finally I need to add my whiskers. My whiskers go to the min and the max that are not, I repeat, that are not the outliers. You do not take the whiskers and take them all the way out to the outliers. So I need to look back at my data set one more time, and looking at the top end, I see that the last piece of data was the outlier, 2.55, and the next piece of data is 2.46. So right here, 2.46 is where my whisker goes, and if I look at the bottom, I'm going to find that it is 1.09. 1.09. So my whiskers go down to 1.09 and up to 2.46. And that about wraps it up for section 1.6.